y un contrato permanente aquí en el CSIC, así que Tomás se nos unirá este septiembre trabajando aquí en el ICM. Tomás estudió geofísica en Estrasburgo y obtuvo su doctorado en la Universidad de Australian National University en Canberra, Australia, y después pasó a hacer un postdoc en la Universidad de Berkeley en California. Y desde hace unos años es investigador CNRS en la École Normale de Lyon. La especialidad de Tomás son los problemas de inversión o optimización, o problema inverso que llamamos normalmente en geofísica. Y lo que diferencia a Tomás de la inmensa mayoría de los que hacemos este tipo de problemas es que él ha trabajado muy intensamente en utilizar métodos estadísticos para obtener incertidumbres realistas sobre los modelos que se obtienen en estos procesos de optimización o de inversión. Y es de lo que nos hablará hoy, así que cuando quieras.
Pues gracias, Antonio, por la presentación. ¿Se me escucha bien? Sí, muy bien. Bueno, todavía no me atrevo a dar la charla en español, o sea que lo voy a hacer en inglés si está bien. Okay, so I'm going to talk. I've prepared a very general presentation about what I've been working on during these last years with Malcolm Sambridge, and we've been working on these methods for geophysical data inversion. So I'm going to start with a cartoon to a bit introduce the problems, the type of problems that I'm interested in. And this is a cartoon to represent what is an inverse problem in geophysics. And so we have stations, receivers at the surface of the Earth, and we can make measurements like gravity, like with GPS stations, we can measure the displacement of the ground, or we can measure the acceleration of the ground if there is a seismic wave that arrives at the station. And from this data that we observe at the surface of the Earth, the problem is to recover a model of the Earth, here represented by 4 parameters. We're trying to recover the value of these 4 numbers. We have 4 numbers, x1, x2, x3, x4. Maybe we are looking for temperature, composition, or density, and the problem is from the observations at the surface, what is the values of these 4 numbers. So that's a general way to present inverse problems. And of course, here the solution is going to depend on the data, but a big problem here is that the solution is also going to depend on our way to pose the problem, because we could also say that we wanted to recover only 2 values, 2 layers, or we can also decide as a geophysicist that we want to invert for 6 parameters. And so the number of parameters, the level of resolution, the level of information that we want to put in our model completely depends on our choice. So the solution is going to depend on the data, but also on our choice that we make for parametrization. And this is really the problem that we've been working on, and this is what I'd like to discuss about today. And so in seismology, very often we use seismic waves to recover the values of seismic velocity. So we look for the values here of the velocity of seismic waves. But if we are a bit more ambitious, we can also decide that we want to recover anisotropy. Anisotropy is the directional dependence of the velocity of seismic waves. And if we are even more ambitious, we can also say, okay, we want also to recover the attenuation of seismic waves. And so here is, again, a choice. The solution is going to depend on how many parameters we invert for. And so this is the question. How much information is present in our data with uncertainties, and how much information we should be able to extract from the data, how much information can we put in our model. So in what I'd like to discuss today, what we've been working on is a type of methodology where the number of unknowns, the number of model parameters becomes an unknown. So another way to give a title to this presentation would have been when one of the things you don't know is the number of things you don't know. Now the number of things we don't know, the number of parameters in our model is going to be an unknown. We're going to let the number of unknowns be an unknown. And so, of course, this is a general problem that has been studied in computational statistics, in applied mathematics. And here I'd like to show in this presentation how we can address this issue, we can tackle this problem, and how can we apply the methods that have been developed in different areas in the earth sciences. And I'll start with an introduction, and I'll talk about this problem of parametrizing a geophysical model in seismology with an example with the seismic tomography. And then in the second part, I'll show what we have been working on. Okay, so let me start with a brief introduction of what is seismic tomography and what we're trying to do. Here is a map of Australia, and the goal here is from seismic waves, we are going to try to recover an image of the velocity of waves that propagate at the surface of the Earth. Maybe there is a continent here in the middle where the lithosphere is cold and less dense, and the waves, they go very quick, very fast. Maybe there is an area where we have like volcanoes and the waves that propagate more slowly. But we don't know that. We want to recover a map of the velocity of seismic waves. And with that, what we use is earthquakes. So for example, if there is an earthquake in Indonesia, we are going to have a source here, and we have a seismic wave that propagates at the surface of the Earth. We can measure it here in a station. And of course, we know the location of the earthquake, the location of the station. So what we have, we know the distance. And we know also the travel time. We know the time of the earthquake. We know the time where the wave arrives at the receiver. So we know the time. So from the distance and the time, what we have is a velocity. So what our observation is going to be an average velocity of the wave between the source and the receiver. This is what we measure, an average velocity along the ray. And of course, we don't know if the wave was going fast at the beginning and slow at the end. We just have an average. And of course, this is for one ray, but we are going to have a lot of earthquakes and a lot of stations. So we have a lot of average velocities along rays. And from this set of average velocities, we want to make a map of the local velocity. So this is the problem, and it's exactly the same problem that we have in medical imaging. It's a general problem. And so because we only have a discrete set of measurements, we only can recover a discrete set of parameters. And so very often what we do in seismology is we decide to parameterize our image with pixels, with cells. And so here the problem is very simple. From a set of average velocities along rays, we want to recover a set of average velocities, but within cells. What is the average velocity of seismic waves in this location? We want to relocalize these average velocities. And so here you see that the solution is going to depend on the choice that we make for the parameterization. And there is a big ambiguity between resolution and constraint. We can decide that we want to have a coarse parameterization with big cells. And so in that case, you see in each cell we'll have a lot of rays that are crossing. In that case, we'll have a very good solution for the average velocity within each cell because we have a lot of information. So the average velocity within each cell is going to be a very good value. It's going to be very well constrained. This is good, but in the same time, we will have a problem because the resolution is not very good. And in seismology, what we'd like to do is to have we kind of over-parameterize the model. We've put many small cells. So we have a good resolution, but in the same time we miss information. For example, you see there is a little cell here, there is not even one ray that is crossing, so we're really missing information, and the uncertainty is going to be much larger. So, but very often what we do in seismology, we choose to go for a small pixels, a good resolution, but we miss information. The data is not enough, is not giving us enough information. So we need to add extra information that is not contained in the data. For example, if we want to know what's the velocity here, we want to have a value here in our image. We don't have any information, so we need to add extra information. And we do that with regularization. We regularize the problem, we stabilize the problem, and we, for example, we impose to the solution to be smooth. We look for a model here, an image that explains the data, but we want also that the image, we want the image to be smooth. Or we can also impose to the solution to be close to a reference model. And as soon as we do that, as soon as we impose more information, we lose the ability to propagate uncertainties. And so that's really a problem. And so, for example, if we decide that we want a smooth image, to be able to recover values here, we are going also to impose to the image to be smooth here, and so maybe some information may be lost here. So this is really a problem, and the solution is going to depend on these choices. How much smoothing do we add? How much? What is the reference model that we use? What is the level of resolution? And so, to give you an example with a real Earth problem, here is an image of the velocity of seismic waves at the surface of the Earth. This is exactly the same data set. The data is the same, but it has been analyzed and inverted in two different manners with two different types of parametrization. And so these images to study the mantle, they are very useful because we can look at the continent, and we can see cold continents, we can see here the mid-oceanic ridges that are hotter, and this is useful to do science. But you see here what I'm showing is that the solution completely depends on choices that we have made as users. And so maybe if we want to tell a story about, I don't know, a small anomaly that is here in the middle of the Atlantic, it may be useful to publish a figure like that because we may want to interpret that. But maybe here we are actually just fitting the noise, we don't know. And so even though we are using quantitative methods and a lot of data, the solution at the end depends very much on choices that we make and that are arbitrary. And this is really a problem, and we don't have uncertainties here. So this is a way to introduce the problems that we are interested in. And if we want to do science and to understand the temperature and the composition in the mantle, we need to solve and we need to address these issues. And those are problems that are general. And so here I'm showing another example from seismology, but we're not trying to make an image of the Earth. This is the big Tohoku earthquake in 2011, the one that produced the big tsunami in Japan in 2011. And so here from the displacement measured on the continent in Japan from GPS stations, we can recover the amount of slip that occurred on the fault, the finite slip. And again, here is two solutions with exactly the same data set. But you see that depending on choices that we make arbitrarily on the level of smoothing, we may get completely different solutions. And so if we are a seismologist and we are very interested in the idea that maybe the big Tohoku earthquake was rupturing with two different patches that were separated, and we want to push this idea and publish this idea, but maybe we want to choose this solution. But maybe if we are interested, if we prefer the story where we have a big rupture that is continuous, maybe we will choose this solution. And again, there is no way to clearly differentiate with a classical method to differentiate which is the best solution here. So this is a general problem, and to illustrate this problem, there is a sentence that I like very much, and that was written by an astrophysicist 20 years ago, exactly in 2004, exactly 20 years ago, where computational methods to analyze data were starting to appear with the big computers, and in astrophysics they were starting to use them. And so this was like 20 years ago, and Mackenzie, an astrophysicist, said, now we use fantastic telescopes. We use the best physical models and the best computers. But the weak link in this chain is interpreting our data using 100 years old mathematics. And I guess here I'd like to make the analogy with seismology and geophysics. We are a bit at this stage, so we are a bit like 20 years after astrophysics, but we are a bit at this stage where we have fantastic telescopes. And our fantastic telescopes in seismology is like our ability to collect data. Here I've seen that there is a lot of experiments done in the ocean, and also onshore with seismology. Here is an experiment that was done like 10 years ago in the US, where we've decided as a community to put one seismic station at each 70 kilometers. This is US array. And so this is the waves that coming from Japan, from the same earthquake that I was talking about before. This is the 2011 big Tohoku earthquake in Japan, and you see the waves that are coming from Japan. And with array seismology, with a lot of stations, you really can look at the displacement of waves, and you can do a lot of very nice science. And you see here, red and blue shows the displacement of the vertical displacement of the ground, and the horizontal bars are the horizontal displacement. And you see now the waves are coming from the other side, because waves are going all the way on the other side of the planet, and they arrive at the other side. Okay, so we have fantastic telescopes in geophysics today. And now we have also big physical models, and we have big computers. And for example, we now with numerical methods and with big computers, we are now able to compute numerically the wave field in a 3D medium. And so here is an example. This is a simulation, a numerical simulation to simulate the propagation of seismic waves in the Earth. You see here the core mantle boundary. You see that there is a reflection. Here you have also a surface wave that is building up, and you see at the station we can measure the we can predict the displacement of the ground. And this is very expensive computationally, but we can do it now because we have a lot of computers and we have a code to do that, and this is really this has been a progress in these last years in seismology and in geophysics. So we have these models. And a lot of progress has been made. But still, to interpret the data, we are still using old mathematics, and we are still using Gauss-Newton methods to interpret the data. And this is a problem. To interpret our data, what we do very often is we use iterative linearized methods, where we try to solve an optimization problem, where we try to minimize the distance between observations and data data that can be estimated for a given model. We find the parameters of the model M that minimize this function. And to minimize this function, here is a cartoon showing a function in two dimensions with two parameters. To minimize these functions, what we use is we compute the gradient of this function. We compute derivatives. And the problem with derivatives, so if you follow the gradient, you can minimize the function, and you can go down to a minimum, a local minimum. But the problem with these methods, with gradients, is that the solution depends very much on the initial model that you choose. And so, of course, this is a cartoon a bit dramatic, but I'm trying to show that depending on where you start, you may end up at a very different solution. And another way to illustrate this problem is to say, okay, in seismology, we try to recover a model of the Earth. Here, the seismic velocities will be the horizontal axis as a function of depth. And so, and what we do is we look for a small deviation around a reference model. And if the reference model is different, if we choose arbitrarily a different reference model, then the solution is going to be very different. So our solution, again, depends on the data, but also depends on arbitrary choices that we make. Okay, so we have 3 problems. Our geophysical images, they depend on the parametrization. They depend on the initial model, and also as soon as we impose extra information that is not driven by the data, we are not able anymore to propagate uncertainties. Okay, so what I'd like to show now and to discuss and how we have tackled these issues, and I'd like to introduce this transdimensional methods. And transdimensional stands for the fact that we have the dimension of the model space, the number of parameters is going to be variable. And to introduce that, I'm going to use an example that doesn't come from geophysics, but more from a paleoclimatology, and I'm going to use the simplest inverse problem, which is a regression problem. And the problem is very simple. You have a set of points, and we want to fit a line through this set of points. And so those would be paleoclimate data, which is, we can imagine they are like a proxy for temperature as a function of time or depth. And very often in paleoclimatology, we'd like to interpret them as periods where the climate was constant for a period of time, and then you have an abrupt change in the climate. And so you have like here 4 periods where the climate was stable with 3 changes. And so the data are just noisy data around this black curve here. And so the problem is simple here is from this set of data, the question is where are the change points and how many change points do we have? And you see the number of change points here is variable, the number of periods is variable, so the number of parameters is variable, the number of unknowns is variable. That's why it's a transdimensional problem. We don't know in advance the number of things we don't know, the number of unknowns. And of course, if we use a classical optimization problem here to solve this problem, it's not going to work. If we try to minimize a level of fit to the data, if we try to minimize the sum of the squares of the difference between the red points and the black curve, it's not going to work because we can always add more and more and more change points in order to fit the data. If we have 200 data points, we can have a model with 200 change points, and we will explain the data perfectly. And in that case, we will be fitting noise, of course. So you see that the level of noise here is very important because it tells us how much we should explain the data. And so an optimization framework cannot be used here to solve this problem. And instead of that, what we can use is a different way to tackle this problem. It's a Bayesian framework where everything is going to be seen as random variables and with probability distributions. And our data, we are going to see them as a function of the model. So it's the data here, our points are going to be the black line plus some noise. And if we assume that the noise is normally distributed, here we have a random variable, and so then the data can be seen as a random variable. And if the data is seen as a random variable, we can express it mathematically, and if the noise here in the data is normally distributed, so then we have a normal distribution. And so we can write the probability to observe the data for a given m. M is the model, is the Earth, it's fixed. The probability to observe the data, it's just a Gaussian distribution with a standard deviation, And here is a cartoon showing a Gaussian distribution. The probability to observe the data, we have noise in the data, so we are around the data that we would observe for the true model. Okay, so this is a way to represent the probability of observing the data. And the trick here is to say, okay, we are going to keep exactly the same thing, exactly the same equation, but we are going to say now the data is going to be fixed. The data is what we observe, and there is only this. And the random variable is going to be m, the model. And so now we can express this as a function, not as a function of the data, but as a function of the model. And so you see here, so before the data was random and the model was fixed, and this is the cartoon that we have. And now if I represent exactly the same function, but where m is the random variable, now we have a function that is not Gaussian anymore because we have a nonlinear function here. And so this is a nice way to propagate uncertainties here from the data towards uncertainties in the model that are represented with a probability distribution. And our solution in the model will be described by a probability distribution. And this is, this is useful. Here we are not using probabilities here to describe the frequency of a random process like in a frequentist way, but we are using P here, probabilities, to describe the level of knowledge we have about the Earth. We know the Earth is unique, the temperature in the center of the Earth is unique, there is only one Earth. But because we don't know exactly what it is, as a tool, we can use probability distribution to describe our level of knowledge about the Earth. And so, of course, here, as we increase the number of parameters, we are going to maximize this function, and so we still want to add more parameters to increase this probability distribution. But what is going to prevent us to add more and more parameters is the prior distribution. And so when we work in a Bayesian framework, we can combine, we can see that what we want, the solution that we are looking for is the probability of the model given the data, and it's going to be the product of two distributions. The first one is going to be a likelihood distribution, the one that I just discussed, times the prior distribution that represents what we know about the model parameters before looking at the data. And so here is a cartoon to show why this prior distribution is going to prevent us to go to too many parameters. Here is an example with a very simple problem, just one unknown, one parameter. We are in a one-dimensional space. And we are going to say that the a priori distribution for this number, x1, that we're looking for, is going to be not informative, and we are going to say it's a uniform distribution between a minimum and a maximum value. So the value of x1 can take any values here in this range, delta x. And because we are expressing this as a probability distribution, the integral here needs to be 1. The area in blue needs to be 1. So the probability of a given value is going to be 1 over delta x. The probability of any model with any given value is going to be 1 over delta x. And now if I go to 2 dimensions, I add an extra parameter. And now instead of one layer, I'm looking for 2 numbers, 2 layers. We are in a 2-dimensional space, so we increase the set of possibilities, we increase the range of possibilities, and we are able to explain our data better, of course. But you see, because the integral here is still going to be 1, we need to, the value of a given, the probability of a given model is going to be 1 over delta x squared. It's going to be lower. We increase the range of possibilities, but the probability of any specific individual model is lower because they have all equal probability. And so you see that here, as we increase the dimension, we decrease the probability of individual models. So this is a nice way to implement what's known as the principle of parsimony, that says that between two theories or between two models that explain the data exactly in the same way, the simplest should be preferred. If you have an image of the Earth with just one value x0, and you have here an image of the Earth with exactly the same image with just value x0. It's exactly the same image, but one is described by one number and the other is described by 4 numbers. So a priori, the probability of the one described by four numbers is less probable. And so this is what we are going to use to describe, to implement this principle of parsimony. Okay, so now our solution is not going to be, we are not in an optimization framework anymore, and our solution is not anymore a best fitting model. Here we are, if we are in a 2-dimensional space, but it's going to be a probability distribution. So here in a 2-dimensional space, the solution is going to be a probability distribution in a 2-dimensional space, and so we have uncertainties and we have a lot of information. And so it's going to be more complicated than that, because this in 2 dimensions we can make a cartoon, but now we are going to be in a transdimensional space. The dimensions are going to change, and analytically there is no real way to find a solution for that. And so that's why we are going to use Monte Carlo sampling and a Markov chain Monte Carlo sampling to describe our solution. So here, again, and this is a cartoon. We are in a 2-dimensional space. We are looking for the values of x1 and x2. The solution is not going to be the best fitting model here in red, but the full distribution. And to approximate this function, we can use algorithms like a Monte Carlo, Markov chain Monte Carlo algorithms to produce a very large ensemble of models, a very large ensemble of points here that are going to have a very interesting property. They are all going to be distributed according to the function that we are trying to approximate. If there is if the value of the function is high here, we'll have a lot of points here. So if we make a histogram of all these points, we will have an approximation of the function. This is the tools that we are going to use. We are going to use algorithms that produce a large ensemble of possible models, all distributed according to our target distribution. And of course, for that, we have the best fitting model, but we can extract more information. If we want to know what is the value of x1, we can make a histogram of all the values of x1, and this tells us what's the probability of x1 given the data. We have uncertainties, and we didn't have to include extra information that is not driven by the data. Okay, now if I come back to my regression problem, the solution is going to be millions of models here that are representing a distribution. And of course, we have models that fit very well the data, but we have also models that are very poorly fitting the data, but we also need them to, because we're sampling a distribution, and we need to represent also the tails of the distribution. And the problem here is that this is a bit ugly. We have just millions of models, and we don't know what to do with that, but this is the solution. And now an exercise is to extract statistical information from this ensemble. And for example, what we can do is at each location, at each time or at each depth, if this is a time series, we can look at the average. Here is we have the average, which is a red line, and we can also look at the credible intervals, and we have uncertainties. And so you see here this line here in red, the smoothness of this line, the complexity, the level of complexity of this line is not driven, is driven by the data, and it's not driven by a choice that we made as user. There is no smoothing parameter that was determined here to determine the smoothness of this value. And so here in this problem, we were interested in how many change points do we have, and what are the location of these change points. But what we can look at the distribution of these change points. We can look at how many change points do we have in this ensemble. And so this is a histogram of the number of change points in this ensemble solution. And you see that the most probable number of change points is 3. And of course, maybe there is a small chance that we had 10 changes. And if we are interested in the location of change points, we can also look at where are the change points in this ensemble. So there is always this exercise of extracting statistical information from this large ensemble that can be complicated to appraise. Okay, so here is a very simple example with this type of method. This is, again, a regression problem. You have points with uncertainties. And the question is, how do we fit this data? Do we need a constant line, like the blue curve? Or do we need a linear trend described by two parameters, y equal ax plus b, a and b, two parameters? Or maybe we need more than a linear trend. Maybe we need a quadratic function described by three parameters. Or maybe even more, a cubic function. What is the degree of complexity of the polynomial that we want to use here to explain this data? And with this type of transdimensional Markov chain Monte Carlo algorithm, we can sample a lot of models. And so here is the sampling. We're just trying a lot of different models. You see some are quadratic, some are cubic. And so this is constant. Here it is the proportion of the time where we have a linear trend. This is the quadratic function, and this is the cubic. And so we are testing a lot of functions, and at the end we have a solution that tells us the most probable degree for our polynomial here is a linear trend. And we can say, okay, we may want to fit a linear trend here for this data set with these uncertainties. And then on the top of that, we have uncertainties also about our model. Okay, so this was just a way to introduce this type of methods, and of course what we wanted to do is to apply them to our problems in geophysics and in seismology. And a first problem that I'd like to talk about is the problem of receiver functions in seismology, because it's very similar. What we want to do is to recover a model of the Earth, the velocity of seismic waves as a function of depth below a seismic station. We want to recover this model here in red. And so you see it's very similar because we have constant layers in the Earth with discontinuities, and in the Earth we have discontinuities and constant layers. And so the data that we use is the vertical and the horizontal component of the displacement of the ground due to seismic waves that we measure at a station. So I'm not going to go into the details here, but what I'd like to say is from data that we observe at the surface, we can produce a very large ensemble of models here in black that represent our state of knowledge that we have about the Earth model that we want to reconstruct. And from this ensemble, but we can look at an average, and so this is going to be an average model here in blue that follows the average at each depth, and we can extract here a model of the Earth. This is a density plot. It's another way to represent it. This distribution at each depth. For example, if we're interested in what's the value of seismic velocity as at 25 kilometer depth, we have a distribution. And if we are interested also in the location of discontinuities, where are the discontinuities? We can look at the probability to have a discontinuity. And so this is a method that we have used in the last years to image the lithosphere below continents down to 300 kilometers. So this is a probability distribution for the velocity of seismic waves below Canada down to 300 kilometers and below India. And we have been able to combine different data sets. And so I don't want to go into the details of the discoveries that we have made and the geology. And the only thing I'd like to show is that we have been able to show that we have similar structure in different continents. Here in India, in the Indian craton, in the North American craton, and this has been useful to understand the mechanisms for the formation of continents. And I just like to say that these type of methods are useful and they are enabling us to make discoveries in earth sciences. Okay, so now to finish, I'd like to go back to the initial problem that I was talking about, which is seismic tomography, where we are trying to make a 2D or 3D image of the Earth from seismic waves. So I'm coming back to Australia. And so here, because we want a parametrization with change point that is going to be able to vary, we cannot use pixels which are regular, but we are going to need to use a different adaptive parametrization, which is here done with Voronoi cells. So these cells are quite useful because they are only here, this way to partition the space is only described by the position of the black dots. If you give me the position of black dots, we can look at the perpendicular bisectors in blue, and we have a way to discretize the Earth in different cells. And so here, in our inverse problem, the unknown are going to be the number of cells. We are going to be able to add one black point or remove one black point in the Monte Carlo process. We are going to test a lot of models with different position of cells. We are going to also to invert for the velocity value of seismic waves in each cell, and also for the position of the black dots. So if we have a lot of rays in one area, we expect to have a lot of small cells we expect the parametrization to self-adapt to the level of information in the data. If in the ocean we don't have information, we expect to have large cells. So here the parametrization of the problem is not fixed by the user, but it's going to be an unknown in the problem. We invert for the velocity, but also for the way we use to parameterize the model. And so yes, this was the reason why I was showing giraffes and turtles. It's because these Voronoi cells, actually, they have a lot of properties, and they are very useful to use numerically, and they have a lot of nice properties, and that's why they have kind of a universal nature, and you can find them a bit everywhere in nature, in giraffes and in turtles. So here is a synthetic experiment. This is a fictitious model of the Earth that we are going to try to recover with this method. We are going to put some rays. We are going to produce a synthetic data set. We are going to add noise to the data, and we are going to see if we are able to recover this image. So on purpose, we have put a lot of small rays here, so a lot of information will be available here, and a few information will be available in the other side. So we put a heterogeneous distribution of information to see if the parametrization is able to self-adapt to the non-uniform distribution of information. So here the solution is going to be a large ensemble of models here. One model with 11 cells, 20 cells, 32 cells, and the solution is a large ensemble of models. The solution is an ensemble, it's not a single model. We have a distribution. And then we need to extract statistical information from this ensemble. And what we can do here, because we have millions of models like that, at each pixel we can look at the mean value and at the standard deviation. And so if we look at the mean value, we have an image of the Earth here that doesn't depend on the parametrization choices. And if it needs to be smooth, because when we are stacking a lot of models with different parametrization, they are going to the discontinuities, they are going to destructively interfere, and they are going to disappear. But if we have a discontinuity that really exists here and that really is required by the data, by a constructive interference in all these models, we are going to be able to recover this discontinuity. And on the top of that, we have uncertainties, and this is useful, of course, because we have now an image with uncertainties associated to that. And so if we compare this solution to a more classical approach where we optimize the difference between data, and we optimize a function, here the solution with the classical method depends on the level of damping, the distance to a reference model, or the level of smoothing. This is a solution with a classical method with a regular grid. If we compare the transdimensional image here that we can obtain, you see that we are able to recover better the discontinuity, and it doesn't depend on any choice. Okay, so this was a synthetic experiment, and I will just show you quickly some results that we have been obtained. So in Europe now, to study the Alps, we have a fantastic telescope that has been set up, which is Alp Array. We have a lot of seismic stations, and we have been able to make an image of the Alpine Arc and the Apennines here in Italy, and to answer important questions for the formation of the Alps and so on. And we have also used it in the American continent. This is the fantastic seismological telescope that we have in the US. From all these stations, we have been able to make an image. And so this is a work of some colleagues in Maryland, in the University of Maryland. And so here the solution is an ensemble. So this is a movie that's showing you that there is not a single model, but an ensemble of models. If you are in the ocean, you don't have any information, so you have any values that can be sampled. Whereas here in the western US, you have more information because you have earthquakes, and so you have less uncertainty. Another way to look at this another way to look at this, I think I'll pass that. Here is, there are different ways to look at, the complicated thing is that we need to look at this complicated distribution. Here we have, we have a 3D model of the US at different depth ranges. Each time you have the velocity of seismic wave, but you have also uncertainties. And as expected in the oceans, you have a high degree of uncertainties because you don't have information. And lastly, a last application that we are working on is to do that at the global scale and to have a model here at the global scale to be able to study the mantle as a whole and to study the formation of continents and other important questions in geodynamics. Okay, so here I think I'm finished, and to conclude, what I wanted to show you is that there is what we're trying to do in our group is to try to promote this type of methods and to try to show that they can be applied to different problems in seismology, but also in other areas. And so before I finish, I have to conclude. I want to also I'd like to talk about a limitation of this method. So a problem is that we can make a lot of big distributions to describe our level of knowledge, but sometimes it's difficult to communicate and to appraise these solutions. And for that, I'd like to talk about a problem. This is an analogy. Let's imagine we want to predict what the weather is going to be tomorrow. We want to predict two values, what the temperature and the level of rain that we are going to have tomorrow. So we are looking for two numbers, temperature and precipitation. And so if we use the most simplest way to express this solution is to give just two numbers. We can say, okay, here is the solution. It's 1 point. Tomorrow it's going to be 20 degrees, and it's going to rain 10 millimeters. And this is a simple solution. It's simple to communicate because we can say to a 5-year-old kid, okay, tomorrow it's going to be hot and it's not going to rain. And it's easy to understand, easy to communicate. But in the same time, we just have two numbers and it doesn't describe very well our state of knowledge. And if we want to be more precise, we need to include uncertainties. And of course, we should include uncertainties. And a simplest way to include uncertainties is to give error bars, to give a sigma, and say, okay, tomorrow the temperature is going to be 20 degrees plus or minus 1 degree, and 10 millimeters plus or minus 2 millimeters. And so here to describe this state of knowledge, you see that we need 1, 2, 3, 4 numbers. It's a bit more complicated, it's a bit more complex, but at the same time it's more accurate. And so you see that there is a bit of a paradox here, because we can also include more information if we can say, okay, well, we actually have a Gaussian distribution with a correlation. Now we have a correlation matrix, which is described here by 1, 2, 3 numbers, plus 2 numbers. Here's 5 numbers to describe our level of knowledge, which is more precise. It's better because we have correlations. But now it's more difficult at the same time to describe this state of knowledge to a 5-year-old kid, because we will have to say, okay, tomorrow I don't know exactly if it's going to be cold or hot, but I know that if it's hot, it's going to rain, and if it's cold, it's not going to rain. So it's more complicated. And this is still a 2D Gaussian distribution. Now it could be like 2 Gaussian distributions, so this is much more complicated. And what I've shown you is with Bayesian methods, we are very happy because we can sample full distributions. What we actually have is a full distribution. And we are very happy about that, but at the same time, you see that here it will be very difficult to communicate to a 5-year-old kid and to say, okay, tomorrow the weather is going to be this distribution. It's very difficult to interpret. And even when we talk to geologists and who are interested in the depth of the moho and the density of the crust, and if we showed something like that, there is no way to make science with that. So there's really a problem. We are facing a paradox. We are happy to have distributions, but we don't know how to use them yet. Yeah. And so this is a problem that is important. And yeah, to finish, I'd like to show you that. So this is an example of a last model of a global model of the Earth, but we should remember that when we look at a model like that, obtained with classical methods, we are still using methods where we are just looking at one point and we don't have uncertainties, and this is also a problem. Okay, thank you. I will stop here now. Thank you.
Okay, first of all, Thomas, thank you very much for the talk. It's quite, I think, wide and basic, and I think that many people can understand a little bit what is the potential of the method, and then to think on their own field how it could be applied, if it's something that could be interesting. So it's very nice, and thank you also. Welcome, man, welcome. We are very happy that you arrived here, and I think it's fresh air and different ways of looking at the things, which is very important because you have worked a lot on methods, and this is something on mathematics, and this is something basic that we think that we are lacking in our group and probably in the institute at different levels. So you are very welcome for this. Then I enjoyed the talk, and I have a general question we can discuss afterwards. As you probably know, we work quite a lot on tomography, but mostly a different method, but one that we have been developing for a long time is the 3D travel time tomography, including both first arrivals and reflections to invert for the velocity field and the geometry of reflecting boundaries. Okay, then we pick the travel times and this in 2D and now in 3D. And there are different levels of complexity. There is also anisotropy, things like this. But this is the tool that we have, and now it can include also earthquakes. But normally the way we try to calculate uncertainties that we know that it exists is basically the uncertainty that comes from the initial model we choose and also the picking errors that we have in the different phases. So we do some assumptions on this, so the distribution of initial models on the distribution of the picking errors for the phase, for different things, and then we generate an ensemble of initial models, and then we get different final models, and then we calculate the mean or the average deviation at each point of the model, and this is an estimation. But we know sometimes, and just by doing this with synthetic models, that okay, it's a proxy of the uncertainty. We can say the places where it is best resolved and worst resolved, but it's not really a measure of the real uncertainty. It's good, it's much better than having nothing but this. And my question is, knowing the problem that we work, because what we are not interested in the model itself, but for example, the typical problem that we are interested in, I am now interested in, is in subduction zones, having an array of OBSs, having active or passive data, and using all this to have a model of the velocities, and especially the velocities and the geometry of the interplate boundary. So having better models with a much better estimation of uncertainty on this particular problem would be very, very good for us. And I don't know if it's something that we can discuss to adapt these Bayesian models at this particular problem with this particular. So I don't know if I explained myself.
Yes, understood that. Yeah, and yes, of course, and this is also, yes, this is what we've been talking about in these last days, and I think that will be very nice to apply this. So what I've shown here are application to ambient noise tomography and mantle tomography. But of course, the methods are general and could be applied to more small-scale problems, like crustal problems, and as you were mentioning. And the interesting thing about the problems that you're mentioning is that you are interested in discontinuities. And so it's at the same time velocities and discontinuities. And this is something that from my side I find very interesting, because with this adaptive parametrization we can invert for both at the same time, let the discontinuities and the velocities vary. So this is definitely something I'm interested in. And the only question is going to be how much does cost the forward model, computing one ray, because we are, as I was showing, we produce a lot of models. And I didn't say that much, but it's expensive. So we need to be able to compute a lot of times the forward model.
The forward model is parallelized, but it's a combination of the graph method and then bending. So it's not the fastest one, but it's quite precise. That is we could discuss.
Yes, exactly. So this is the time. Exactly. And sometimes it's good to go a bit down in the complexity of the forward model and to use a simpler forward model to be able to have an inversion that is better able to manage uncertainties and then increase the complexity of the forward model. We have to play with that, and this is the things that we'll have to discuss. Yeah.
Was a comment about this. I wanted just to ask you about this topic, because one of the limitations that I understood with these methods is solving the forward problem, because you need millions of models.
Yeah.
So in our field, we have to invert, we have to resolve many ray paths. So I was wondering if anybody in the community has actually attempted to apply these methods in this kind of problems, like that we have thousands of forward problems to resolve. I don't know.
Yes, there are different. Some people have even tried to do Monte Carlo sampling with spectral element simulations, which sounds a bit crazy because spectral element simulations are very expensive. But if you are in a setup which is quite simple, and you don't have that many rays, and you have a problem that is quite specific and local, and you have one question, then it can be done. Also, you have also techniques where instead of trying to model at each iteration the entire data set, you can decide to just randomly choose a sub-sample of the data set. If you have like 1,000 data points, each iteration of the Monte Carlo sampling, you are just going to try to look at the fit to 50% of the data set. And you change it randomly each time. And so this is really interesting because you have a lot of methods that are developed in the area of computational statistics, and we can look at them and say, okay, maybe we could use that for our problems, and So those are interesting problems and questions. Yeah.
Thank you. It was very educational.
Okay, thank you. Yes.